Okay, everybody, March 8th, 2026. I thought what I would do is go over a fire behavior nomogram for a fuel model 2 for timber with grass and understory. And this one here is set up with the low wind speeds, which down here you can see goes anywhere from 0 all the way up to 7 miles per hour. This particular fuel model has a dead fuel moisture component, and then it has a live fuel moisture component. And then you see the symbols of the firefighter and the dozer. It's important to point out that this shows an upper limit of flame lengths and rate of spread of what a dozer from the 1970s would have been able to handle, which basically was predominantly the open cab type dozers. So I don't believe that this is going to be a limiting factor anymore. However, it's important to note where their positions are. So anywhere from probably 8 chains per hour to as much as 22 chains per hour for the average firefighter, and then upwards of 42 to 48 chains an hour for the dozer. Just something to keep in mind. I again don't believe that that's going to be a limiting factor. So let's talk about what we got here. So we got 4 quadrants. We've got down here, we've got a percent of slope, anywhere from 0 to 120%. And remember, 100% is a 45-degree slope. So we're probably talking closer to a 60-degree angle, almost 70-degree angle at 120% over here. So what this is used for, this quadrant here, is used for determining your effective mid-flame wind speed. So you get your slope in percent, and then you'll go up to your observed winds. And then let's say, for example, you're 60% of slope, and you go up and you record it in your local area at 10 miles an hour, and then you'll slide over and you get a wind speed. You might make a note on the left-hand side here and then jot that down, and then that would then be transferred over to here. If your wind speed is higher than what you have here, then you'll have to flip from the low wind speed side to the high wind speed side. So that's just something to think about. Then that's what you would do with this quadrant again, is transfer your wind speed from here over to here. And then you would draw a diagonal line like what you see here. And if it doesn't exist, so let's say you come up with a wind speed over here of 3.5 miles an hour, then you would start from this corner. And what you would do is you would take a ruler and you would approximate and draw a line. I've got this laminated, so I would use a dry erase marker and you would just draw a line and then make a note 3.5. Then once that's done, what you do is you come up to your dead fuel moisture percent, and let's say your dead fuel moisture is at 4%. So how this works, because you've got a dead and a live fuel moisture percent, you'll notice that dead is 0 to 14, or actually 15. And then from over here, it's 0 to 14. So you got dead on each side. So you would take your ruler and line it up 4 and 4, draw a line with your dry erase. The purpose of that is to show you that that is an upper limit, that your line should not go above that. Then what you have is these, which look like S curves. These are various live fuel moisture percentages, from usually 50 to 100 to 200% of live fuel moisture. This is also called the moisture dampening curve. Also, these are live fuel moisture percents, okay? So if you've got, let's say 120% live fuel moisture. Well, if it's in between 100 and 200, then you would draw a line approximating, and you can only get so close. This is just estimation, so it doesn't have to be precise. You draw it in between there and put that there. So then you come over here between 100 and 150, and you would draw a line approximating 120%. So we're going to walk through this. I'm just giving you a brief overlay of what this all is. This quadrant right here, the upper right, is really the critical component, because you start here And then at 4%, you go over to your live moisture dampening curve, whatever your live percentage is, and then you come straight down. You'll see here that this is your heat per unit area in BTU per square foot. You got 0, 1, 2, 3, 4, 5, 6, and then 700 BTU per square foot. That's what this is showing you. Dead fuel moisture percent. These right here are your BTU per foot per second figures. So from 5 to 20, 5 to 60 to 100, 200, 300, 400, 500, etc. These up here are your flame lengths, your estimated flame lengths in feet. This is your rate of spread in chains per hour. And that's pretty much it. I will point out also that if you take note, fuel type, timber, grass, and understory, this is your carrier within the timber component. But the fuel type and the dead fuel moisture percent up to your live determines your BTU per square foot. Wind speed and slope are going to determine your rate of spread. And then you combine those two to get your intensity along this line. So let's go ahead and work through this problem right here. And I think what we'll do is we will flip this over and go to the high wind speed side. And let me see if we can get this here real quick. Okay, so everything is lined up and looking good. Okay, so right off the bat, we'll say that we're at a 60% slope. Okay, and we're going to say that we've got a 12.5 mile per hour wind speed. So you'll note that you got 10 and then 15. So each intermediate line is 2.5 miles an hour. So that's going to be your 12.5 mile an hour wind speed. So how you would work this is take your ruler, estimate it as close as you can. You're going to go up to 12.5, and you're just going to go up about right there. As soon as you get to that line, you will stop, and then you will make a 90-degree left turn and go over to there. So now you know you got 10, 12.5. I would say we're probably at about a 13 mile an hour wind. So what we'll do is we'll put a 13 and circle that. Once we're done with this, okay, now we take that number, and blue is often used as an input color. So then what we'll do is we'll take, and let me move this. We'll come over here, so you see 12.5, and then here's 15. So like I was saying, what we'll do is we'll estimate where our 13 mile an hour wind speed is going to be. And we'll just say that it ends up right about there. And then we'll put 13, and then we circle it. And when we circle it, and this is what you find that they go over in like S490, you circle it to let people know that's come up and looked at your nomogram, that you've actually looked at it. It wasn't just a number, you factored it in, it's going to be used, okay? Now, for a dead fuel moisture component, let's say, since it's grass and then understory, we'll say our dead fuel moisture percentage is going to be 3. So let's go to 3. Okay? 3, 3. And so our live fuel moisture component, let's say that that is at 100%. So that'll be that center line right here in the middle. So what we'll do then is, now that we pretty much got this, we got one more thing to do, and that is our live. So our live is going to be at 51, 152, 253. This is like 300%. So we'll leave it right there for a second. Let me switch something here. Yes. Now I can see it. I had to switch classes here, guys. So 50, 100, 152, 250, 300. So we're going to say that our live fuel moisture is going to be this line right here at 100% live fuel moisture. Okay? So now we're done with that. So what you could do is put 100 and then circle that to let people know that that's the line that you're working at. Now, switch colors. Now we're going to start drawing our outputs of what this fire is going to be doing. We're done with this quadrant over here. So now what we do is we go from our 3% and we'll come down at our 100, which is going to be that. And we're going to try to line this up as straight as possible as we can. And it looks like it's going to be right about there. And then we're going to draw down. And you'll note that it's hard to see now, but you got 400 and then 600. So that's probably going to be about 520 BTU per square foot. However, you continue the line all the way down to our effective wind speed of 13 miles an hour, and then we're going to make a turn. And that turn is going to be off in a 90-degree direction, and it is going to go this direction to this diagonal line right here. That's called a turn line. In fact, every line that you're drawing is technically called a turn line. So we continue it up, and we try to line this up. I like to be as precise as I can, but you don't need to be. This is just to estimate and give yourself a benchmark or a baseline. Anybody out there that's an EMT, you know you take blood pressure and respirations and all that jazz to establish a baseline for your patient. Well, we're doing pretty much the same thing right here. And then what we do is we come over, and then that's what it should look like, is just like that. So now, right now, I can tell you right now that we're at like 525. I'm going to call it 520. Yeah, 525 BTU per square foot. That's going to be my HPA. So HPA equals 520. Okay. Now, our rate of spread looks like it's going to be about 210, because in the middle will be 250 chains per hour. So each line is 25 chains per hour. So it looks like it's going to be about 210 chains per hour. So we'll put ROS 210 chains per hour. Okay. So we can now. So I'm writing it down, but we'll go over it. I'll draw another picture so you guys can see here. So now, at this point right here, this intersection right here lets us know that our intensity in BTU per foot per second is between 2,000 and 2,300. So I would say that that's going to be about, 2,150 to 2,200 BTU per foot per second. So let's say that, let's call it 2,150. So our intensity will be, so intensity equals 2,150. Okay, that'll be our BTU per second per foot. That's how that's supposed to be. So that's supposed to be BTU per second per foot. Okay, 210 chains per hour. So I'll get a different sheet and show you how this breaks down. And then we follow this line up, and we can see that our flame lengths are between 14 and 16 feet. Okay, so actually it's going to be closer to 15-foot flame length. So that's going to be your flame length right there. Intensity 2,150, flame lengths 15 feet, and rate of spread 210 chains per hour. So now I'm going to break this down. Oh, let me show you this. So again, you start off with getting your slope percentage and your observed winds to get your effective mid-flame wind speed at 13 miles an hour. Take that number, transfer it over here. Okay. Again, we switched to the high wind side because 13 miles an hour wouldn't fit. The other side only went up to 7 miles an hour. Okay. So now, once that's done, we factor in what our dead and live fuel moistures are. So we figured dead at 3%, drew the line, and then we figured that we would use the existing 100%. Now, in reality, your fuels lead or technician is going to get fuel moistures, and that live fuel moisture percent is what you would be cataloging and drawing lines approximately in here. A good way to use this is to use a line lower and a line higher, and then you can do another plot and you can determine what the effects are going to be. You don't have to use these for just one plot at a time. So at any rate, so that's what this is. So now what I will do is take this and move that out of the way. And where is my sheet? Okay. So now we had a rate of spread equal 210 chains per hour. The BTU per second per foot was 2150. Now, to make this worthwhile so that you understand how to determine what the rate of spread is in feet per second, which is what fires move at in feet per second. So take your ROS equals 210, multiply that by 66 feet. So 210 times 66, that equals 13,860 feet per hour. And then if you divide that by 3,600, it will equal 3.85 feet per second. So that is the rate of spread in feet per second. So now, if we have 2150, and let's say that our fire intensity, we want to determine that. So fire intensity is going to be this 2150 times the fire line length. So let's estimate that. Let's say you got a fire line that you estimate about 1,500 feet. So it'd be 2150 times 1,500 feet equals 3,225,000 BTU per second. Okay, so right off the bat here, the way to use this number in determining resources is you have to understand what water absorbs. So 1 gallon of water at 5,000 feet of altitude and 50 degrees Fahrenheit temperature, that's water temperature, will absorb 9,366 BTU per gallon. Or if you're working with a nozzle, a 60 gallon per minute inch and a half nozzle, it's 9,366 BTU per second because 60 gallons a minute is 1 gallon per second. However, if we want to find out how much water we need for this, then what you do is you'll take this number and divide it by the 9,366, which means you need 340 4.3 gallons per second. Now, here's the catch or the trick. If you can find an aircraft such as a seat that carries 800 gallons and they can drop that water over the 1,500-foot distance of the fire and you have other resources there, you just snuff that out. So that is pretty much it in a nutshell on how to use this. You can use this again as your baseline to determine what resources you're going to need for your particular fire. Keep in mind, this is for your carrier fuel. So you might be having different fuel types and different densities in there. If you think that a fuel model tool 2 for your timber with grass and understory is not cutting it, uh, go up to the next fuel model that's going to have a little bit more BTU volatility and try that again. This is a baseline to say, hey, this is what we think the fire is going to do. This is what we think the fuel type and moisture is going to be, and then try that. But that's how I would use these and the nomograms so that you can determine what you need. Again, once you get your intensity of your fire, if you divide it by 9,366, it will tell you how many gallons you need per second. However, it doesn't have to be every single second. You can segment this out and say, okay, we can't cover the 1,500 feet of the line. We've only got a Type 3 ship with a 180-gallon bucket. Well, that's fine. With this figure right here, you could probably get this with 3 Type 3 180-gallon buckets, because each 180-gallon bucket on a helicopter is 1.7 million BTU worth of cooling capacity. So understand that there's a very big benefit to knowing how to use these old tools from the 70s, which are still much applicable. The arithmetic is still being used today, only we use it in software. But if you laminate these and keep them with you, you can do a really good, quick and dirty, estimate your intensity and your flame lengths or whatever, see if it's matching with what you're seeing on the fire line, and call resources based upon the intensity and the output of what this fire is doing, and then you'll be able to determine this. Another thing that's good with this is that it will let you know whether or not your nozzle can achieve this on your engine. For example, if we had well, let's say that we had a similar situation, but the fire was calling for, let's say, 15 gallons per second. So right there, that doesn't seem like much. But if you take 15 and multiply it by 60 seconds, that's 900 gallons a minute. Now you're talking about, 900 gallons a minute. Now you're talking about something that rivals 1,000 gallon per minute, 1,250 gallon per minute pumper trucks. They're not going to be able to follow much anywhere in the wildland environment, and even so, they would need a serious lake or a river to be able to pull water out of. So even this number right here needs to be carefully considered with what you're looking at. Remember, 1 gallon per second equals 60 GPM. And that's pretty much it, guys. Hope this helps, and I'll see you on the next one.